This Thursday, day after tomorrow. Yeah. So we'll have some more technical stuff, and then at the end we'll have a 20 minutes of review for the final or so. So fracture mechanics really started in about 1921. There was a guy, Griffith. So he was an aeronautical engineer. And if you remember 1921, this is just a few years after World War I. And really, it was sort of the birth of aviation. And World War I was sort of the first time that planes were more than a novelty. You know, they were used for something. And of course, then with that became the issues of how do we keep these things flying as they age. And the particular problem that exists to this day in terms of airplanes is fatigue cracking. Right? Cracks occur. So how many of you think when you fly on an airplane there's no cracks in it? I hope they're not, but there's cracks. There's definitely cracks. There are lots of cracks. And the idea is to understand how they're going to propagate well enough that you can predict them from, rupturing in a violent way. A couple of years ago, just 2-3 years ago, there was a Southwest plane that had a rupture, right? And it sort of, no one was hurt or anything, but it tore a part of the fuselage off, and they had to make an emergency landing just 2-3 years ago. And it had it associated with fatigue cracks that were forming. So a lot of the work that's been done in fracture mechanics is motivated by aircraft because you have to build them out of lightweight materials so that they fly, and then these lightweight materials will, eventually, because things are thin and other things, you eventually get cracks that form. And so we want to understand how they propagate to prevent anything catastrophic from occurring. And there was a guy, Griffith, who did a bunch of experiments where he'd take a sample with a crack in it. So he had a cracked sample, and usually when we talk about in fracture mechanics, there's pretty much a convention that, and don't ask me why, but when the crack has 2 tips, then its length is 2a, versus if a crack has 1 tip, then its length is a. Right? I don't know why that's the convention, but it is. So when you have a crack, say length 2a, and you apply a far field stress, so we'll call that, the stress of loading. And what he noticed was that for a range of different materials, that the point at which the sample would rupture, meaning it would, break into 2 pieces, crack completely through, was a constant value that was proportional to the stress of loading, the far field applied stress, and the square root of the crack length, A. And so he did a bunch of experiments, and in fact, this 1921 paper, you can download it. Right? It's still, it was presented to, I think, the British Royal Society, and I think I have a copy of it on my computer, likely, because I've referenced it many times. So, so with that kind of idea in mind, let's see if we can sort of make some energy arguments about what may be occurring, so that we can come up with, basically we want, if this is always a constant value, right, for a different material, then you might think that this is some material property, right? Just like we have material properties, Young's modulus and Poisson ratio, there might be some material property that's associated with fracture, okay? And so I'm just sort of going to come up with a hypothetical thought experiment here, but if we have a sample with our crack 2A, we apply a far field stress, and you might imagine that, from a static analysis that you have some weight, and so as you increase the weight, then this applies a stress that's higher and higher, right? So it's really a force, but if you divide it by the width, then you have a stress, right? And so you have the sample itself, you have some elastic energy in it. So you might think of this like a spring. So from kind of a static analysis, you might think of that this is a spring connected to something, connected to another spring, connected to a load, right? You probably solve problems like this in statics. So this spring in the bulk of the material, well, this is energy associated with the elasticity of the material, right? So I can take a metal or even a piece of rock, right? Metal's more easier to think about because I can stretch it a little further, right, before it fails. But even a rock, I can take it and I can pull on it a little bit, and it'll have some elastic response. And so there's some energy associated with that. And so what we're going to do is we're going to write down. He looks like he's hungover. He's been asleep. So if we're going to write down basically an energy balance, so the total energy in this mechanical system over here has some energy associated with the elasticity of the material, right? Plus some energy associated with creating new surfaces of the crack, right? So that's what this something in the middle is there's two surfaces there, and when we create new surfaces, we dissipate energy, and so this is an accounting for that energy. And then the work done due to loading, okay? And so stated in words, like the conservation of energy says that like the time rate of change of energy or the change in energy with respect to something is equal to the energy created minus the energy stored, right? So thermo stuff, right? So here we're going to sort of make an argument that the total change in energy associated with a change in crack length is equal to 0 due to this energy balance. So basically, we're going to take the derivative with respect to the change in crack length of both sides of this equation. And I paired those up because that's sort of the mechanical energy, the energy associated with the elasticity of the material. So this is the energy associated with creating new surfaces, and this is the energy associated with mechanically loading the material, our system. And this thing is going to be equal to 0. And so the work due to loading, I mean, from Physics 101, what is work? Force times distance, right? So exactly, it's force times distance. And distance is, displaced distance. So we could also write that as force times the change in length, right? And force is nothing more than the stress, the far field stress, times the area. And another way we could write change in length is to write the strain times the length. And that comes from the fact that our definition of strain, right, is strain in an engineering sense is the change in length times over the length, right? So delta L is equal to strain times the length, okay? Sorry. Can't remember. There's a trick where I don't have to do that. I can't remember. So that's the work due to loading. Then we also have the so-called strain energy. So this is the mechanical energy stored in an elastic body, right? And what that is sort of the area under the stress-strain curve, right? So for an elastic material, stress-strain curve is just a straight line with the slope E, right? So it's the area under this. So the elastic energy is 1/2. I'm just doing an area calculation here. 1/2 base time height, right? So at the load applied, that's the area under the curve. Then we also want to include the volume, right? So this is actually an energy density. So it's really, this has units of work or energy per unit volume. So then if we multiply the volume, then we have something like that. So if we look at the work per load and divided by the energy, then you have something like this. And that's equal to 2. So another way to say this is that the work due to loading, external loading, is 2 times the strain energy. And so then if we plug that relationship back in, then our energy balance simplifies to the energy associated with creating new surfaces plus this guy, or the energy associated with creating new surfaces must be equal to the change in strain energy with respect to length. So we're going to define our energy associated with creating new surfaces as 2, because there are 2 sides to a crack, 2 surfaces on a crack face, right, a top and a bottom, times 2A, because that's the length of our crack, times some specific surface energy. So this is sort of something called specific surface energy times the width. So if we divide by the width so that we have the energy associated with creating new surfaces divided by width, then that's equal to 4A gamma. Then the strain energy of a cracked elastic body divided by the width is equal to pi a squared times the far field stress times 1 minus mu squared over E. And this comes from a solution, Inglis, 1923. So it was a paper by this guy, was able to write that down. And this is for plane strain. Plane strain. So we haven't really talked about plane elasticity in this course, but sometimes you can, under certain scenarios, you can simplify the full 3D elastic equations to 2D under certain scenarios, one of them being plane strain. So plane strain is actually the scenario which we derived equations for stress on an earlier homework assignment. But this is the idea that the body is so thick in one direction. Its one direction is so thick that the strain is essentially zero in that direction, right? Because, again, strain, so you can imagine, like, if we're talking about strain in the z direction, is delta L over L. But L is so large that this is approximately zero, right? Because L is so large compared to any amount of change in L. Then this is called the plane strain problem. So typically plane strain, or when you have things you approximate as two-dimensional that are really, really thick, right? A lot of times we do this in hydraulic fracture simulations. We take a plane of the Earth, which is really thick in the vertical direction, right? And then we look at how fractures propagate in the 2D plane. That's not always a good assumption with hydraulic fracturing, but because the height, essentially when you do that in hydraulic fracture, you're assuming that the height of the fracture is infinite, and it's not. So you sort of have to correct for that. Okay. So now we have basically the strain energy divided by width and the surface strain divided by width. We can multiply, on both sides of the equation, we can multiply by width and then do our energy balance. So our energy balance for a gamma. And you get this. So we typically call this guy something called G. G is known as the strain energy release rate. Okay. So in words, what this is the total amount of potential energy required to open up a new surface, okay, a new fracture surface. And if you were to go into the lab then and say do a set of experiments, take a large two-dimensional plate that's thick so that our plane strain assumption holds. We have a small crack in the middle of it. We apply a far field of stress, and we do this repeatedly. What you would see is that there would be some critical far field stress that if we did it enough times, statistically there'd be some critical value that it occurred all the time. Right? And when I say occurred, it actually ruptured. It broke into two pieces. Right? Then this would be called the critical value of critical value of strain energy release rate. So that critical value of strain energy release rate, that's a material property. I took a derivative. And so there was a 2 in front, but there was a 4 over here. Right? So I took a derivative, so that left 4 gamma on this side and 2 pi a on this side, right? Then I divided the 2 out, and I got 2 gamma. Okay. So this thing is a material property, or if you go to the lab and you were to do these types of experiments and measure this repeatedly, then you could define, at least in a statistical mean sense, some critical strain energy release rate that would be a material property. Okay. This is a material's resistance to fracture, essentially. And then just one last sort of, if we look at just this part and we rearrange it such that we have this. So I just rearranged the equation, right? Well, if you have ever had fracture, you wouldn't know this now. If you have had a fracture mechanics course, you would recognize this thing right here as the stress intensity factor, which is typically what we talk about. We don't really talk about strain energy release rate as a material property. We typically talk about stress intensity factor. And so this term is the stress intensity factor. And then that from this, then we have a relationship between the stress intensity factor and the strain energy release rate. So, if you measure one, there are different experimental setups that can give you one or the other, but just know they're related. And so next time we'll talk more about the stress intensity factor. But the stress intensity factor is important because with knowledge of the stress intensity factor, we can determine what the stress field is anywhere near a fractured tip, right? So if we have a fracture and we define if this is the tip of a crack, and we define a coordinate system in terms of polar coordinates from the tip, so where this is r and this is theta, okay? And we're interested in the stress field out here in front of the fracture tip. Remember, at the tip of a crack, at the tip of a moving crack, it's basically a moving discontinuity in displacement. Right? You have a displacement jump there. And if you remember what the mathematical definition of strain is, mathematically strain is a derivative in displacement. Strain is a derivative in displacement with respect to space. So at the tip of a crack, that's undefined. This derivative is undefined, okay? And then, of course, stress is some function of strain. In the simplest case for elasticity, stress is like this. So stress is also a function of the derivative of displacement, which is undefined at the tip of a crack, right? So stress is, in fact, according to this theory, what this means is that it's actually infinite at the tip of a crack. Well, we know this is not physical. No material can withstand actually infinite stress. So there's sort of a hole in the theory of elasticity at the tip of a crack. And so fracture mechanics was invented to sort of fill that hole. And the way it works, or the way is that you solve asymptotic solutions, okay? And all of the information about the stress of the crack is contained in this critical, in this stress intensity factor. And so what you can work out is that the stress, the full stress tensor, so the ij components of the stress, are a function of the stress intensity factor over 2 pi r times some function, some dimensionless function of theta. And so this over here is a dimensionless function. It doesn't contain any material properties or anything like that. So all of the information about the stress near a crack is contained in the stress intensity factor. That's why it's sort of an important thing when it comes to fracture mechanics. And so, what the model sort of predicts is that, as you go, you can see just from this, the stress as a function of r, square root of r, right? So as r moves away from the crack tip, and if this is stress as a function of r, as you move away from the crack tip, since it's the square root, you're going to have this decay behavior. But at the crack tip itself, it's undefined. So the crack tip would be 0, R0. Okay. So a little bit, next time we'll talk about then, a little bit more about stress intensity factors and how that we can use them to sort of predict fracture trajectories in hydraulic fracturing events.